for the invitation and for the possibility to speak here. And I'll present the results on a joint work with Maciej Malibowski. And Maciek is about to finish his PhD at Jagiellonian University. And so we are at risk to lose one of our experts in high-performance computing. Okay, and well, I find Einstein equations at negative cosmological constant an exciting subject, and I agree completely with Louis that in spite of almost over 15 years of activities in AdS CFT, I think this subject is still unexplored from the GR perspective. And one aspect of this is that negative cosmological constants allows for time periodic solutions of Einstein equations. So in this talk I present to you two independent methods of constructing such solutions, one perturbative and one numerical. And in the simple model, which is massless scalar field minimally coupled to Einstein equations at negative cosmological constant with spherical symmetry. But well, I think this simple model is just an illustrative example of more common phenomena, that is the existence of time periodic solutions in wave equations, nonlinear wave equations on bounded domains. And in the AdS case, I think these solutions completes our understanding of AdS instability. So, well, our motivations come from the conjectured instability of AdS space. So, as Piotr told you in the morning, well, some time ago we gave some numerical and heuristic evidence that the AdS solution AdS space may be unstable against black hole formation, well, under arbitrarily small, quite generic perturbations. But at the same time, we knew as well that there exist initial data that do not collapse and that seems to stay forever close to AdS or some other solution. And subsequently, the similar conjectures were made by Santa Barbara group, and with the recent work by Louis and collaborators on AdS, on boson stars in AdS, and our time periodic solutions, I think now there is an evidence that you can have asymptotically AdS stable and regular solutions in Einstein equations. So my task is easier because Piotr has already introduced the model to you, but so I'll go just very briefly. So, well, we parameterize the asymptotically AdS metric at spherical symmetry with the following ansatz. So we have two metric functions, A and delta, and well, T is time coordinate, X a compactified radial coordinate, which goes from 0 to pi12. And that's, well, this is spherical symmetry, so these two metric functions, A and delta, depend on T and X only. And so to generate dynamics with spherical symmetry, we need to add a matter of, well, we generate the dynamics by adding to the system massless scalar field minimally coupled to Einstein equations. And then, well, from the Einstein equations, we get these two constrained equations for the metric functions. And for the Bianchi identities, the equation of motion, we get the equation of motion for the scalar field phi. And here, for the later convenience, I introduce some auxiliary variables. Well, the capital P, which is proportional to the time derivative of the scalar field, and capital Phi, which is special derivative. And the derivatives will be denoted with primes and dots for special and time derivatives respectively. Okay, so this, well, the advantage of this ansatz is the equations that comes out looks very simple. comparing, for example, to what Franz showed you in the morning. And well, they're not too difficult to solve. And of course, if you take the scalar field to 0, the metric function A to 1, and the metric function delta to some constant, you recover well-known AdS solution. Okay, and well, this system can be integrated in time once the boundary conditions are set, because as you know, the null infinity of AdS, of asymptotic AdS space, is in causal contact with the AdS space itself. So, well, at spherical symmetry, it's easy to introduce the mass function of the system, and the total mass of the system can be read off from the fall off of the metric function A at the boundary. So, well, then in this model, the boundary conditions are set in the way that we insist on the total mass to be finite, and also we want to have a smooth evolution. And in this particular model, this leaves no choice for and the boundary, well, the boundary conditions we get are effectively reflecting boundary conditions for the field, with a suitable fall off of the field at the boundary, which in our coordinates is located at x equal to pi half. Okay, and as we learned in the morning as well, with such boundary conditions, the problem is at least locally well posed in time. So it makes sense to study it. Okay, so maybe, well, if we linearize the system of equation around the pure AdS solution, we get a wave equation on a fixed AdS background that was studied extensively by Ishibashi and Wald. And, well, the spectrum of the corresponding linear operator is composed of integer numbers, positive integer numbers. So the AdS is linearly stable, and this spectrum is fully resonant. This means that these integer numbers form an equidistant ladder. And well, the corresponding eigenvectors that were referred to as oscillons in Louis' talk in the morning are expressed in terms of Jacobi polynomials, cosine 2x, in other coordinates. Okay, so this is at linear level. And well, as Piotr told you, well, when we study the system in full generality, the initial data usually collapse to a black hole. But for example, if you start with single oscillon initial data, then in full setting, the solution is not longer periodic in time, but it does not collapse to a black hole. So the idea was, if we try to look for some, well, first what we wanted to do was to understand this behavior. And then the idea was, well, maybe it's possible to look for, to use some perturbative scheme to understand better. And finally, well, there was also the influence of Santa Barbara group. We looked for the time periodic solutions in our system. And the strategy is as follows. So we start with a single oscillon in our initial data, but to make the solution periodic, we know that we have to add some more, to excite some more oscillons of the initial data as well. So we expand our solution in the following way. We include one oscillon in the leading order. So epsilon is the, let's say, the amplitude of the so-called dominant mode in the solution. And we have to correct this solution in higher orders. And we do it perturbatively. That is, well, we construct the solution order by order, perturbatively construct the solution order by order in epsilon. Well, it's convenient to rescale the time variable. So because, well, we know the frequency of the oscillon, but we do not the frequency of our time periodic solution. So we rescale the time variable in that way that we absorb this unknown frequency into the time variable. When the frequency, unknown frequency, well, it starts with the dominant mode frequency, and then there are some corrections, perturbative corrections that we have to determine. And well, similarly, we expand. Now we expand the fields, the scalar field, and the metric functions in a power series in epsilon, the amplitude of the dominant mode. So, well, in the limit when epsilon goes to 0, our solution reduces to a single oscillon. Okay, so this is the ansatz. And now at each, okay, and we know that the oscillon basis forms a complete set. So every function can be expanded in the series of, in the oscillon basis. And more importantly, if the number of special dimensions even, this base is well adapted. So it means that each order of perturbation expansion, now we use this basis. So we, at each order, we expand the corrections to the scalar field and to the metric functions in the oscillon eigenbasis with a coefficient that now, well, we insist on them to be periodic in our rescaled time variable. And well, this works well in even D, as for D, well, there are some technical problems, but well, we are sure that the solution still exists. Okay, so then maybe for later convenience, I'll introduce notation. So I'll denote the natural scalar product in the on this set of these functions this way, and as I will solve the system order by order, I will denote the coefficient at some power epsilon in the power series expansion function f in that way. Okay, so well, perturbatively, in general, what we do, we plug our ansatz, the equations, and do it order by order. So linear constraint equations, that's easy. That's just some linear algebra to solve. So probably I will not go into detail, but well, this is nothing more. But then the corrections for scalar field are more involved. As in each order in lambda, when we calculate the corrections to the scalar field, we get an inhomogeneous wave equation with a source that depends on what has been previously calculated in lower orders. So now, as the oscillons form a complete set, we can expand the corrections in the oscillon basis, plug into the equations, and then project into oscillon functions. And what we get that's the first harmonic oscillator equations for the coefficients in the expansions. So I will remind you that, well, if you have first harmonic oscillator with its own frequency omega naught and some deriving term, well, its frequency omega, and we set the initial conditions for the solution, then the general solution can be put in the following form. And we see that if the frequency of the oscillator itself coincides with the frequency of the driving force, we get secular terms. That is, the terms which grow periodically in time. And such terms would spoil the periodicity of the solution. Okay, and we get such resonant terms and such secular terms in the solution whenever the ratio of these two frequencies coincide for a given coefficient coincide with the frequency present in the source. But the main idea here is to use, first we have three parameters in the expansion for our frequency, unknown frequency, omega. So, and also we have the undetermined integration constant. And the main idea is to use this freedom, the frequency of the solution, and the integration constant to kill the resonant terms in the source, order by order. Pomodoro started. Okay. Okay. Well, and the magic is that you have exactly enough constant, unknown constants in your solution to do it at each order, step by step. So, the procedure closes. And the only limit which is set is the computer resource you have, the memory of your system, because then the whole algorithm is implemented in the Mathematica. Okay, so that was the sketchy way of perturbative construction of such periodic solutions. So now let's move to another method, numerical one. And here, the starting point is we rewrote the equations to allow for efficient spectral integration. And the main point is that, again, we use the oscillon basis to represent the field and its momentum at some time t. So, we expand the field and the momentum in the oscillon basis. And this basis is well adapted to the problem, while this coefficient fall exponentially. So, it's safe to cut this expansion at some finite k, capital K. And, the spectral code, what it does for you, you supply, the coefficients of your expansion at time t, and it produces for you the time derivatives. And then you can integrate them in time. So this is the evolution code. But we use this piece now to construct the time periodic solutions numerically. And we do it in the following way. So now we assume, again, first of all, again, we make the same time rescaling, and then we assume that our time periodic solution can be expanded both in the oscillon basis and in time periodic functions. And again, the method will work well if we cut, the coefficients are cut exponentially, so we can cut the sums at some finite numbers. And so to find the equations, now we have to find the solution by finding 2 times k times n unknown numbers for these coefficients, fij and pij, this number of unknowns, plus one unknown number, which is a frequency hidden here. So now we can set our system on the grid, and as I told you, our spectral code allows us, if we know the coefficients of the modes in the solution, the code will produce for us their time derivatives. So we can compare on the grid the time derivatives computed from the spectral method, and the time derivatives obtained directly from taking the time derivative of this ansatz. So this will constitute, 2 times chi times n equations for both one, because we have equation in time for phi and capital pi, and we are missing one equation, and we add it as our condition for a dominant mode. So we want our dominant mode to scale as epsilon. Dominant mode to scale with epsilon. And well, that way we get a high nonlinear system, but it can be easily solved with Newton-Raphson algorithm. So these are 2 completely independent methods that do not know one about the other, but it seems that they produce the consistent results. And okay, I have 5 minutes left, so maybe I just quickly show you the results in a Mathematica notebook that Maciek prepared. So first of all, well, let's look how the solution looks like. Yeah. So for example, well, this is the result of perturbative calculation. So we have to code in Mathematica, and then you just supply the number of dimensions, the number of dominant mode. You wait for some time, and for example, this is what you get for the frequency expansion. And well, this is not a closed form, but I think in computer era it does not matter really. So okay, so this is the frequency. This is, for example, the scalar field. So we start with, well, this is a solution built on the fundamental mode. It's the dominant one. So it's order epsilon. We excited only one mode, and then each subsequent auto-ordering epsilon, we excite a finite number of eigen or oscillons. And so these are the perturbative results. And as cross-check, well, you can calculate the total mass. You do it directly by plugging the solution into definition. It looks like that, but you know that it should be time-dependent. Yeah? So let's ask Mathematica to simplify this expression. And it really is. Yeah? Okay. So now let's move to numerical solution. So again, we represented the solution in the following form as a double series in oscillons basis and in harmonic functions with some coefficients which depend on the amplitude of the dominant mode in the solution. And so we start with a single mode in the solution, and these are subsequent coefficients obtained numerically. So this is log-log scale, so you see that they fall exponentially. That is nice. Well, here the amplitude is a very small number, but well, you see that as you increase the amplitude, this is still exponentially cut. Yeah? So, well, this is a good representation for the solution. And, well, of course, at some point, this procedure will break down. It's about this value. And, well, we'll see in a moment why. Oh, why at this value. And, okay, so that was, these were 2 independent methods of constructing time-periodic solution. But now the question is, are these solutions stable? Yeah? Because, for example, this numeric method will work, well, if you have a good starting guess, it will find even unstable solution. Yeah? So, well, this is not a proof, but I think strong numerical evidence. So what do? We construct the initial data with our procedure, and we put them to our evolution code and see what happens. Yeah? And this is, let's say, some cross-section of the phase space. So the solutions, well, the field and the momenta are expanded in the oscillon basis. So here we make a parametric plot of the coefficients of these on these oscillons. Yeah, and as the solution is time periodic, these curves should close after one period. And well, this is, you can choose, this is for example for the coefficient, the oscillon, well, 33rd oscillon in the momentum and 37 in the field. And you can watch a movie, and you know, it closes, yeah? And this is the result of evolution of, well, maybe not thousands, but hundreds of periods. So, and if you solve the problem numerically, you always introduce some numerical error. So, well, I'm pretty sure that the solution is stable, because otherwise you would see it. Okay? So, okay, so I have 2 minutes left, so I just, okay, so from perturbative procedure, we have a series representation. So now, well, first what we try to do, we try to, okay, so then you can ask whether this series is, or this is represents some analytic function, or this is only asymptotic series. And well, it seems that the radius of convergence of our solution is greater than 0. And well, to show it, we use, now we have a series representation for the frequency, and we can try to accelerate the convergence of the series with the Padre method. Yeah. So, well, for some values of epsilon, the dominant mode, we have some numerical results on the frequency, some results from the direct sum of the perturbative series up to the order we are able to calculate it, and then we accelerate with the Padre method. Well, with the order of polynomials in the, well, symmetric Padre with the order 2, 4, 6, and 8, let's say. And these are the positions of the nearest, well, the smallest 0. So this is, let's say, the, okay, so first of all, if we accelerate the convergence with Padre summation for small values of the perturbative parameter, we get an excellent agreement between the two methods, which is up to 26 digits of precision. And again, if you look for this estimate for the radius of convergence, well, it seems to converge to some value, which is, let's say, it's 0.09. And, well, accidentally, we do not understand why, it also coincides with the threshold for a black hole formation. Because, of course, if you exaggerate with the epsilon, the stuff will collapse almost immediately. Okay, so results were presented. So we get time periodic solutions and 2 ways, and the 2 methods are consistent with each other. And also, there is a strong evidence for the stability of obtained solutions. Okay, so yes, so this is, well, the next conjecture, or next challenge to prove if these solutions really exist. And well, we are pleased as now I think we understand the behavior of this one mode initial data that we studied 2 years ago. And also, I think we understand what Louis was talking about, this window in sigma of our data UR parameters. So, well, it turns out our understanding is that there is some range in sigma where the initial data we studied approximate quite well the time periodic solution, which seems to be stable. So let's say this family of initial data lands of some stability island of AdS. Okay, and it seems to be quite common phenomena, which actually Maciek Malibowski studied as part of his PhD thesis. Okay, thank you.
So you said there was some technical issue in odd dimensions. Is it related to the fact that the Green's function in even dimensions stays on the light cone, but in odd dimensions it goes off the light cone? So you mix different periodicities?
Well, in this setting, well, these oscillons are solutions to a wave equation on a fixed background. And they have some boundary behavior, yeah, that you cannot be read off on the formula. And then you look at the boundary conditions your field should fulfill at the boundary. Well, at the slides there was only leading terms, yeah, but then you go to higher terms in the extension. And it turns out that if the mass of your system is not zero, well, this oscillon basis is well adapted or have the proper boundary conditions only for even number of spatial dimensions. In odd number, well, the parity in higher order expansion does not match. It matches only the limit when you take the total mass of the system going to zero, so on a fixed AdS background. So this means that if you use such basis in your spectral code, well, it's overkill, yeah, because you get a polynomial decay. So you should include much more terms to get accurate results. But well, you're pretty sure that well you can do it. Yeah? You can obtain some approximation and then put it again to your evolution code. It seems periodic, yeah? But you are not able to get such amazing accuracy. But this is, I think, just a technical issue. But well, I think it should be kept in mind. So the problem itself is complicated. So if one studies it, it's much better to study it in 4+1, 6+1, and so on, and not to start with 3+1, which can be misleading.
Okay, thank you very much again.